Good day, everyone. Today we'll be presenting on graph theory in social networks and future advancements. This research explores how graph theory applies to social network analysis, its challenges, and future potential. Graph theory has become a cornerstone in understanding social networks. This presentation covers its applications, such as community detection and centrality measures, while addressing challenges like scalability and privacy. Additionally, we will discuss emerging trends like privacy-preserving techniques and fake news detection. Ultimately, this research highlights the evolving role of graph theory in addressing real-world problems. Graph theory studies the relationship between entities represented as nodes and edges. It's particularly vital for social networks where nodes represent individuals and edges represent their connections. Social networks are complex and graph theory helps node models and analyze their structure and dynamics, providing insight into behavior and communication.
Basics of graph theory. So graph theory is a branch of discrete mathematics that studies graphs, which are structures consisting of vertices and edges. These graphs are illustrated as diagrams where nodes are represented as dots or circles and edges are represented as lines or curves connecting them. Now, graphs are classified under two main things. So there are directed graphs and there are undirected graphs. So in an undirected graph, edges have no direction. For example, if there's a vertex that represents people at a social gathering and an edge means they've shaken hands, this relationship is mutual, so the graph is undirected. However, in a directed graph, edges have a direction. So for instance, if an edge indicates that a person A owes money to person B, the relationship is one way, making the graph directed. Now, let's talk about the types of graphs under social networks. So there are several types of graphs, particularly relevant to social networks. So back again on directed graphs. So these represent one-way relationships, like following someone on Twitter. Directed graphs can be strongly connected, where every vertex is reachable from any other vertex by following the edges. Weakly connected, where vertices are connected if edge directions are ignored, or it can be disconnected if no path exists between some vertex pairs. So now let's talk about undirected graphs. So these represent mutual relationships, such as Facebook friendships, where connections are bidirectional. A graph is connected if every pair of vertices is reachable. If it's connected to at least one pair of vertices, these represent mutual relationships such as Facebook friendships where connections are bidirectional. A graph is connected if every pair of vertices is reachable. It's disconnected if at least one pair of vertices lack a connecting path. Now let's talk about weighted graphs. Here, each edge has a numerical value such as the strength of the connection between the distances from either of the nodes. Let's talk about bipartite graphs. Bipartite graphs, these have two sets of vertices where edges only connect vertices from one set to the other, like a network linking users to their edges. Path graphs, these arrange vertices in a linear sequence connected by edges. Cycle graphs, these form closed loops where the last vertex connects back to the first vertex. Now multigraphs, these allow multiple edges between the same vertex, representing repeated relationships. Then we move on to the properties of graphs. Next, bipartite graphs. These have two sets of vertices where edges only connect vertices from one set to the other, like a network linking users to their edges. Path graphs. These arrange vertices in a linear sequence connected by edges. Cycle graphs. These form closed loops where the last vertex connects back to the first vertex. Now multigraphs. These allow multiple edges between the same vertex, representing repeated relationships. Properties of graphs. A degree. This refers to the number of edges connected to a vertex. For graph with loops, a loop counts as two edges. A path. A sequence of distinct vertices connected by edges, where each vertex is visited only once. A circuit. A sequence that starts and ends at the same vertex without repeating edges. Examples include the Euralian circuits, which traverse every edge exactly once, the Hamiltonian circuits, which visits every vertex exactly once. Now a cycle, a closed path where the first and last vertices are the same, but all immediate vertices are distinct. Connectivity, a graph is connected if a path exists between every pair of vertices, otherwise disconnected. The foundational concepts in graph theory are crucial for modeling and analyzing social networks. By understanding the different types of graphs and their properties, we can better study the relationships and structures within these networks. Thank you.
Applications of graph theory in social networks. Graph theory plays a foundational role in understanding and optimizing social networks, enabling us to unravel complex interactions and behaviors. Let's explore some key applications. 1. Community detection. Community detection algorithm uses graph theory to identify clusters of users within a network who share common interests or interact more frequently with one another. These insights are invaluable for improving recommendation systems, such as suggesting friends on Facebook or tailoring content on platforms like Instagram and YouTube. For example, Netflix uses similar techniques to recommend shows to groups who share similar viewing habits. 2. Centrality measures. Centrality measures such as degree centrality, betweenness centrality, and even eigenvector centrality help identify the most influential individuals in a social network. These individuals act as key nodes for spreading information, making them crucial for designing effective marketing or viral campaigns. Think of influencers on platforms like Twitter or TikTok. Their prominence in network amplifies the reach of products or ideas. 3. Network evolution models. Graph theory helps us understand how networks grow and evolve. One well-known phenomenon is the rich get richer effect, modeled by preferential attachment. This explains why certain nodes, like celebrities or high-profile accounts, continue to attract disproportionate attention and connections over time. It helps businesses anticipate trends and allocate resources effectively in a dynamic online environment. 4. Shortest path algorithms. Shortest path algorithms in summary, graph theory is the backbone of social network analysis, from clustering users to amplifying influence, modeling growth, and optimizing connectivity. It enables social platforms to operate efficiently while delivering personalized and meaningful experience to users. Thank you.
Graph theory algorithms play a crucial role in understanding and enhancing social networks. Examples of graph theory algorithms include PageRank algorithm. Initially developed for ranking web pages, it identifies influential nodes in social networks by analyzing the quality and number of inbound connections. It supports recommendation systems and ensures efficient handling of large networks using techniques like damping parameters. The second graph theory algorithm we want to look at is friend recommendation algorithm. Methods like breadth first search, depth first search, and link prediction use graph structures to suggest new connections. These algorithms leverage proximity, mutual friends, and community detection to improve engagement and build meaningful user interactions. The next algorithm we want to look at is graph traversal algorithm. The breadth first search and the depth first search explore network structures for tasks like community detection, relationship mapping, and influential analysis. Breadth first search is efficient for finding shortest paths, while depth first search uncovers cycles and dependencies. Now, there are some challenges and limitations involving the use of these algorithms. 1. Scalability. Massive social networks require a distributed computing, graph compression, and dynamic algorithms to handle growth and real-time updates. 2. The next challenge includes complex relationships. Certain graph models oversimplify human relationships, failing to capture temporal and contextual dynamics.
Case study of graph theory in social networking. Case study of graph theory in social networking can be found in 4 major social networking platforms, namely Instagram, Twitter, LinkedIn, and Facebook. You might say, oh, how are they used under these various social platforms? Well, on Twitter, it's used in the sense of hashtags. The more a hashtag trends, in the sense that the more a group of people like a hashtag, the more it becomes popular and the more people are put on it. So the algorithm works in the sense of, if you like something and a lot of people like something, you guys are placed in a group and similar things of such are suggested to you. It also works on Instagram in the sense of the like features. You might be saying, oh, why is this person popping up on my Instagram feed when I don't follow this person? You might not follow the person, but the person might be doing something that you like. You understand what I'm saying? Then it can also work under LinkedIn. So LinkedIn does it in a special way, in the sense of they do it on their sign up page. In the sense of when you sign up, they tell you your age, your level, entry level, what you're looking for, your experience. In that sense, they're already putting you in a social graph, in the sense that it helps you reach other potential people. They don't give you something advanced or way out of scope of what you're already comfortable with. They give you something similar to what you're comfortable with. That's the way graph theory in social networking works under LinkedIn. You can also find it in ads on YouTube, where they suggest ads that you might supposedly like. So those are some of the few things you might get under social networking in graph theory, and those are just the few exciting case studies out there. Thank you.